For half a century, the tech industry operated on one incredibly simple rule. If you want a faster computer, just make the transistors physically smaller. We've pushed that rule to its absolute limit. As we enter the sub-3 nanometer, or angstrom era, the physical gates inside these chips are approaching the size of individual atoms. At this scale, physics actively rebels. Electrons begin to phase right through solid barriers in a process called quantum tunneling, causing massive electrical leakage. To control this leakage and keep shrinking components, foundries are forced to build machines of staggering size and complexity. The procurement costs of extreme ultraviolet lithography, the extreme cleanroom environments, and the sheer drop in yield rates mean the actual cost of printing a single transistor is now climbing. Shrinking a piece of silicon is no longer a sustainable route to cheap, fast computing. The industry has hit a wall. Climbing over it requires an entirely different way to measure progress. Look closely at this two-dimensional silicon wafer. Packing billions of logic components onto a flat plane means the connecting wires become incredibly thin and long. This creates the RC delay bottleneck. As interconnect wires narrow, parasitic resistance, the friction-slowing current, and capacitance, the stored charge, spike exponentially. Even with more gates on that surface, signals struggle through resistant wires, creating a literal data traffic jam. We are manufacturing microscopic, hyper-fast logic gates, but the system as a whole is choking on its own geography. To bypass this physical blockade, Huawei recently introduced a new principle for semiconductor design called the Tau scaling law. The strategy is straightforward. Stop obsessing over the physical dimensions of logic gates and start shrinking the time it takes signals to move between them. Signal propagation delay is governed by the time constant, tau, resistance multiplied by capacitance. To make chips faster, you must compress that equation. But how do you reduce resistance and capacitance if logic gates are stuck on opposite ends of a flat two-dimensional board? These limitations are purely geometric. Solving them requires moving beyond the constraints of a flat plane and breaking into the vertical z-axis. Huawei's solution is LogicFolding. Instead of laying components out side by side like a sprawling city, it breaks apart the traditional planar layout. Logic units that normally sit far apart are separated and stacked directly on top of one another, then fused together using microscopic vertical bridges. By converting a long horizontal journey into a microscopic vertical drop, the physical distance the signal travels is virtually eliminated. The resistive and capacitive loads drop accordingly. You end up with double the processing density within the exact same packaging footprint. The entire system speeds up, not because the individual gates were shrunk, but because the space and time between them was optimized. The pursuit of lower latency scales upward from the level of microscopic transistors to the architecture of massive enterprise AI data centers. At the data center level, the bottleneck is no longer a single wire, but the physical distance between thousands of individual processor chips. To manage this, Huawei developed Unified Bus, a system designed to connect NPU chips within their Atlas SuperPOD clusters. Unified Bus redefines how these nodes talk to each other, using native memory semantics to drastically cut communication latency. It mirrors the philosophy of LogicFolding by shortening the functional path between data and processing power. By eradicating these systemic delays, an entire supercluster of over 8,000 chips can overcome internal traffic jams to operate as a single, unified brain. This shift moves the industry's strategic focus. For decades, the primary bottleneck was front-end manufacturing, the extreme lithography machines required to carve logic gates on a horizontal plane. Now, technical value is concentrating in back-end packaging. The new priorities are high-depth etching, extreme chemical-mechanical polishing for wafer flatness, and complex 3D integration. This technology is moving from theory to mass production. The first smartphone chips utilizing this vertically stacked LogicFolding architecture are scheduled for release in the fall of 2026. The roadmap accelerates quickly. By 2031, chips designed with this 3D time-scaling method are projected to reach transistor densities equivalent to traditional 1.4 nanometer processes. They achieve this density and performance entirely without relying on the spiraling costs of further geometric shrinking. The path for computing power has changed. We have reached the point where making things physically smaller is less important than making the time between them shorter.